Welcome back, students. This is the one compartment open model part 2 of the video IV infusion case. So in the previous class we had done up to this expression which states that C concentration term is equal to R naught upon clearance 1 minus e to the power KET. Now this was the general expression for one compartment open model IV infusion. Based on this, if we make a graph having plasma concentration on the y-axis and time on the x-axis, we get such a graph in which we see that after the beginning of infusion the concentration slowly rises up till a point reaches, let us mark this point as A and this point is point B. After this point a steady state concentration is achieved. How does this happen? See, what happens is that at the onset the amount of drug in the body is more than the elimination. The meaning is that initially the amount of drug in the body is 0 before infusion starts, which means that the elimination will also be 0. As the amount of drug in the body increases, the rate of elimination will also increase, which means that initially the rate in is going to be more than the rate out, or the elimination is less than the infusion rate. A point is reached when the rate in becomes equal to the rate out. That is, the rate of infusion is equal to the rate of elimination. This point is called as the steady state, marked by CSS. CSS, that is steady state concentration in plasma, which is given by this straight line, the plateau or the equilibrium state. After this, when the infusion is stopped, a decline in concentration or elimination is achieved. This graph is similar to the bell-shaped curve which we have studied earlier in pharmacokinetics. Now, what happens at the steady state? Let us consider at steady state. See, at steady state the rate in is equal to the rate out, which means R naught is equal to KE X. How does this happen? See, let us see once again. R naught minus KEX is equal to 0, or R naught is equal to KEX. On converting this expression R naught is equal to KEX into concentration terms by replacing X is equal to VDC, what do we get? We get R naught is equal to KE into VD into C. Now, we can also replace this by CSS and this X by SS, because we are talking about the steady state. Now, R naught is equal to KE VD into CSS. We can write C is equal to, or the concentration steady state is equal to R naught upon KE VD, or R naught upon total clearance. What is R naught? R naught is the infusion rate and CL is the clearance. So the steady state concentration is equal to R naught infusion rate divided by the clearance. Now, on moving forward, this is another expression that we have. On replacing the value of R naught upon CLT, look at this expression from equation 1, R naught by CLT. We can substitute the value of R naught by CLT from equation 1, and what do we get? We get C is equal to CSS 1 minus e to the power minus KET. C is equal to CSS brackets 1 minus e to the power minus KET. Integration and rearrangement of this equation, we get CSS minus C upon CSS is equal to e to the power minus KET. Converting into log form, converting this into log form, what will we get? Log of CSS minus C upon CSS, complete log, is equal to minus KET upon 2.303. This is the final expression for one compartment open model IV infusion. Now, if we make a graph, please carefully have a look. If we make a graph of the log expression, log CSS minus C upon CSS versus time, this is a semi-log plot, we get a straight line with slope equal to minus KE upon 2.303, which means again from a semi-log plot we can determine the value of elimination rate constant or KE. This is the final expression, final derivation for one compartment open model IV infusion. Please go through it once again. Contact me for any doubts. In the next class we shall learn about loading dose, maintenance dose and one compartment open model extravascular administration. Till then, stay safe, keep studying.